Hi, everyone. So we are very privileged to have our very own Misha Belkin over here today. And he is I guess, the foremost authority in theory of deep learning. Although like Misha has been working on machine learning and other areas of applied mathematics for a long time, and he has a very impressive body of work, starting from his works on Laplacian eigenvectors, then a lot of work on kernels, Gaussian mixture. So it's a really distinguished body of work. Misha has won numerous awards and accolades, including the NSF Career Award, multiple Best Paper Awards, and I remember that Misha graduated from U Chicago in math. So yeah, we are very happy to have you, Misha. The floor is yours.
Thank you very much for the introduction, Harry, and yeah, very nice to be here. Thank you. I would like to talk about what I think is probably the most important aspect and the most mysterious aspect of machine learning, modern machine learning, which is this puzzle of dimensionality and some steps that we are taking sort of toward understanding what's happening. And this is, I should start by saying, this is joint work with Daniel Bigelhoff, part-dependent Iteratively Krishnan and Dmitry Sviatsky, who did amazing work on this. And sort of, if you have followed anything which happened in the real, the last few years, it is very clear that mathematics is transforming the world. Deep learning methods, so LLMs, which are, just mathematical formulas, not even that complicated, basically matrix multiplications and nonlinearities, can now do all these amazing things, which until just maybe a couple of years ago, we thought were way out of reach for any artificial intelligence method. And the amazing thing, even though these are mathematical formulas, we don't really understand how this works. We don't understand how, when, or why they work, and what are the fundamental principles on which they're operating. And I wrote a kind of short note about this, arguing that it is, if we want to have any sort of control over the system, or in terms of the safety, the controllability, interpretability, we basically have to understand theory of machine learning. So, well, what is the puzzle of dimensionality here? And I think which is kind of a central question for such a theory to exist. And the fact is that we are faced with similar high dimension, images, speech, text, they're all high dimensional inputs. And in fact, you can argue that few phenomena are low dimensional, and even those usually come with time series, so effectively high dimension phenomena. Now, the key question here is that how do we make sense of high dimensional world, given that things which are intrinsically high dimensional are not explorable, and they're not explorable in a sort of strict mathematical sense. And the classical view here is that dimensionality must be carefully managed, while the modern take on this is that we can sort of just take it for granted that the things are high dimensional and not worry about it. Now, let me just start with a very simple example to sort of give an idea of why dimensionality is such a big issue. And the example would be something like an LLM type-based model. This is roughly just GPT 3.5 or something like that. So you have words, a sequence of tokens, which you can just think of words. And what the model does, I'm not talking about how it does it, but basically what it does is computes conditional probability of the next word given previous 4,000 words. This is known as the context size of 4,000. Now, if you predict this probability, then you sample from that probability distribution for the next token, and then you shift the window by one, and then you repeat the sample the next one, shift by one, sample the next one, and so on. So this is actually nothing else but a traditional Markov chain. You're predicting the next token, probability given by the previous token, and then you're shifting. This is order 4,000, so that's much higher than what we are used to, but it is just a Markov chain. And the prediction is purely one token at a time, and actually training is also one token at a time. It's trained out of regressive. It's what's called self-supervised learning, which is to know to predict the next token from the previous context. Now, why is this a little bit shocking that something like that works? Well, there are several reasons, but maybe the easiest way to see it is to just think about dimensionality of this model. So if this is a Markov chain, so let's just assume that the context size is 4,000 and you have about 50,000 different types of tokens, that so-called vocabulary size. Then the size of the matrix that we need to fill is 50,000 to the power of 4,000 times the number of outputs, which is 50,000. So that's the dimensionality of the space, right? So of course, something with that dimensionality not only cannot be written, but doesn't really exist anyway in the real world. This is far more than sort of any imaginable, like physical number of objects that you can have. So very surprisingly, we can actually recover something like that. That's what these models do, from only about 1 trillion data points. So if you think about like all text that these models are being trained on, it's about between maybe 1 trillion and 10 trillion of that order. So you may think that 1 trillion is a lot of data. So usually it's kind of presented in a way, well, this is trained on all the data in the world, and this is true. But all the data in the world are nothing compared to this. So what is going on? Well, if you think about it, well, let's take one more step further, and let's think, well, suppose I want to explore a d-dimensional space. And what do I mean by d-dimensional space? Well, I have a system with d degrees of freedom. Then how much data do I need? Well, if these are true degrees of freedom, I need, at the very least, I need 2 data points per degree of freedom. So I need like e to the d data points overall. What does it suggest? Well, this suggests that if you have 10 to the 12 data points, then the maximum number of degrees of freedom you can derive from this is log of 10 to the 12, which is 30, a little less. So that means the dimension of all languages in the world, not all languages, but all languages in which it is fluent, principle. I'm talking about languages. It's, of course, now the models are multi-models. Well, images and applications as well. But let's just concentrate on languages. It's about 30, which is a very, very low dimension. So on one side, you have 30. On the other side, you have this humongous matrix, larger than, the size of the universe and so on. Okay, so what does this imply? This means that underlying data and subsequent representations, right, whatever the ways this data are represented in the model itself, right, in the parameters of the model, must actually have very low intrinsic dimension. Somewhere that 30-dimensional space must exist. And furthermore, well, this actually leads us directly to ask the following questions. Well, first, what is this latent space? Where is this 30-dimensional space? How do neural networks reduce dimensionality? Where do they store this 30-dimensional space? And finally, can we somehow figure this out and do something better than the existing neural networks? So that is the premise of what I'm going to talk about, and it's based on these 2 papers. One with Aditya Krishnan, Daniel Mikhail and part dependent when we sort of identify at least part of that mechanism for neural networks. We call it the neural feature ansatz. And that is, which actually shows that this idea, in fact, can recover some classical methods for problems like low-rank matrix completion. And this is with Adit and with Diva Drosvatsky. So let's start sort of with the basics. Well, first learning from data, well, we have data xi and yi, and we can kind of think of this xi being a feature space, like some sort of very high dimensional, and we want to predict response. I'm just writing it as real numbers, but you can imagine some sort of several outputs. What do we want? We want to find f such that f of xi is approximately equal to yi on future data, the data we have. That's the problem of generalization. Now, what kind of methods have been used in the past? Well, if you kind of think about traditional methods, well, what is dimensionality reduction? Well, these are methods like PCA, MDS, multidimensional scaling, things maybe more recently like manifold learning, something I've worked on. And so this is for the data for X. And for the class of hypotheses, you can imagine you can put constraints like sparsity, so you have some basis, and you assume that your representation is sparse in a certain basis. So only a few coefficients are non-zero. And the other possibility that it's something like a bounded ball in some functional space. So another way to sort of control complexity of the data. And sort of what we have seen in modern practice is that certainly we see very high ambient dimension. Certainly linear is not enough. There is very important nonlinear structure. That's on the X side. On the H side, on the hypothesis side, parameter spaces are typically quite large, a lot larger than what classical considerations would suggest. And we usually don't use any sort of explicit norm control or sparsity control or anything like that. Whatever control there is comes from the algorithm direct. There are some exceptions to this, but this is really typical. And finally, we see that in a lot of these cases, although not clear this is the case for large language models, they fit very close to exact fit. So they often fit well below the noise. Okay, so now let me sort of very briefly remind you what the kernel machines are, because that will be important for the discussion that we have. The idea is the following. So you look, so if you're not familiar with reproducing Hilbert spaces, that's okay. You don't really need to know what it is. But so there is basically this underlying space H. And you fit the data such that the loss function on the data, on the training data, plus some sort of norm in the H, which measures essentially complexity of the function, is small. Like you take our mean of this. And the beautiful thing here, that's why we don't really need to think too much about this infinite dimensional spaces, is that for many cases, we know that kernel explicitly, and the upshot of this is that F has this explicit representation as a linear combinations of kernels. Meaning, well, for example, if it's a Laplace kernel, F simply has a following form. It's some alpha I e to the minus norm xi minus x. So we can sort of forget about all this infinite dimensional stuff and simply fit these alphas. And it turns out that for this problem, fitting alphas is simply solving a linear equation. So this is a very clean and nice setup for doing a lot of guiding problems.
Yeah, is the form of the kernel directly related to the norm that is on there?
Yeah, so this space and the form of the kernels are directly related. Right. So each kernel and the space, including the norm, and one-to-one correspondence. Okay. All right, then. So then there is actually quite a lot of literature on this going back to the splines. kernel machines, support vector machine. Very recently, it was shown that wide neural networks trained with gradient descent under certain conditions actually also are this type of systems, which is kind of was a remarkable result. Well, personally, I was very happy to see this because suddenly, okay, like now we know what neural networks are doing, and we can have some sort of mathematical view of that, much simpler than actually thinking about those neural networks per se. Turned out that things were a little bit more complicated. But yeah, so what is special about neural networks? Well, as I said, well, in some regimes, they're just those kernel machines, and we can, in fact, write those kernel functions explicitly. But it turned out that this is not always the case. And in particular, I think one kind of finding was that neural networks seem to have no issue with high input dimension. Well, no issue, of course, with an exaggeration, but much less issue than you would expect. And on the edge side, actually, it turned out to be a quite interesting story. And now I think that we understand better, is that there is this idea of some sort of benign or even obligatory high dimensional overfitting, high dimensionality. So we can even prove mathematically that in some cases, at least, having high dimension is good. So you're having much more direction, the number of data points is beneficial. Okay. So the kind of main thing I'm going to talk about in this talk is how neural networks learn relevant direction. And I'll describe what relevant directions are. And I'll sort of explain like different aspects of this. One thing that I think it's kind of nice because this is when I talk about feature learning, this is what that's relevant directions. And let me start with the following experiment to demonstrate this. So I'll actually show a bunch of experiments and then describe some algorithms, but a lot of it is experiments. And here is a very simple experiment. You take X from a normal distribution in dimension 100 with identity covariance. And now Y is simply the following. I take the sum of the first 5 coordinates and multiply it by the sum of the next 5 coordinates. Okay? This is what's known as an index 2 model. What is an index 2 model? Well, if you think about what this does, if you know this direction, which just the sum of the first 5 coordinates and the sum of the next 5 coordinates, then you can do a projection onto the span of these 2 vectors. That would be a rank 2 operation. And then the product of the things is a quadratic polynomial. So it's a combination of a projection and a quadratic polynomial. So index 2 corresponds to the fact that there are 2 independent vectors. You need a projection to a 2-dimensional space. Okay. Now, if I take 4,000 training points from this, notice there is no noise on Y. It's deterministic. Then I use a kernel machine, and I see that the result R squared is 0.25. So remember, R squared, 0 is bad and 1 is good. So it's like square loss, but the other way around. 0.25, which is not very good. If I, however, take a neural network, the R squared is 0.98, which is actually very good, almost nothing. So I said before that neural networks are kind of like kernels. In some regimes, well, clearly this is not one of those regimes because there is a huge gap between these 2 results. And yeah, any questions about
this? Maybe it's just not the right kernel. Maybe the past theorem is not the right kernel. Maybe it's another kernel.
The answer is no. No, there is no radial.
Or another, just another kernel, not radial. Just...
yes, there is a non-radial. We'll discuss this. Okay, we'll discuss non-radial. But any radial kernels will not do very well. Right.
How many parameters are there in this?
In neural network, I don't remember.
But it's similar for the kernel and the neural network.
Kernel is just the number of data points, which is 4,000. For neural networks, I don't remember. But you cannot like
It's the same order.
kernel. I don't remember, but it's I don't remember. I can't say. But it's a small. I think it's just a full eight. It's a simple. In any case, surprisingly recent, right? The first experiment is like 5 or 6 years old for this type of problem, which is remarkable because this is such a, in a sense, a very, very simple-minded experiment. All of this stuff existed like, 30, at least 30 years ago. Okay. So, well, I should say that there have been real progress in understanding why this is working better. I'm not going to describe this specifically, but basically, there is a line of work showing that, for example, neural networks can learn like single or multi-bit models like this. But really, I'll take a slightly different view on this. So let's think about this now. And the first thing is that, well, suppose now I have a neural network, and let's think about just the first layer of this neural network. Okay. So first layer of this neural network is if the number of neurons in the second layer is D, then it's 100 by D matrix. And you can define this neural feature matrix that's, we call it that, it's sometimes called also neural covariance matrix, which is just W1 transpose W1. And it's a, 100 by 100 matrix. And you can kind of think of this, well, what does W1 do? It's essentially filters the input according to the large eigenvectors of this. But really, you can think of singular decomposition of W1, but it's kind of the same thing. But you can take square root of it. And the claim I'm making is that think of a trained neural net, MLP in this case, as a low-rank filter followed by a nonlinear project. Now I need to introduce the key object, and this is what when I think about feature learning, I have something like this. So you can take this to be a definition of feature learning. So this is this idea of average gradient output product. Now, suppose you have an f. You can think of f being a model, but it's really an arbitrary function the way it's written. You take gradient of f times gradient f transpose, so it's an outer product. So it's going to be, if the input is 100 dimensional, this is going to be 100 times 100 matrix at every point, and you're averaging them over all of the training. Okay? And what does this matrix do? Well, at each data point, it's just a projection onto the gradient, well, a rescaled projection onto the gradient. This 100 by 100 matrix is just projection onto the gradient direction of the point. So this is somehow average projection onto the gradient direction. And if you think about what it does, and it's not completely obvious, but sort of once you think it becomes clear, this matrix measures input directions which affect response for model F. Okay, so in particular, the top eigenvectors of this matrix are those directions that if you change your input in this direction, then the response on average will change the most. And if you have a direction such that AGOP matrix times that direction is equal to 0, that thing will not affect the response. So that's what I mean by feature learning. If this matrix is low rank, then the zero space of this doesn't affect the response. In particular, well, suppose y equals f mx when m is a, say, rank 2 matrix, then you can see that the span of the top two eigenvectors of AGOP will be the same as the span of. Okay, now why is neural net better? And let me show you some actually examples. So remember, I trained this on 4,000 samples. And now look at the neural feature matrix, which is W1, W1 transpose. And compare this to the AGOP matrix, which is what I just described. And you immediately see that they look very similar. They're not quite the same, but they basically have the same structure. Now, what I'm going to do, I'm going to use different filters to filter my data, and then train either a kernel machine or a neural network after on that filtered data. And if I use this neural feature matrix, you immediately see that the kernel, after training the on the data which you first pre-process by NFM, gets very good results at 0.92. Neural network actually is slightly worse, but also pretty good. If you use AGOP, it's even better. Kernel is 0.95 and neural network is 0.92. Now, if you use just a projection on the 10-dimensional space, which is the span of the first 10 coordinates, the result is significantly worse. So the kernel is actually even better for the neural network. I can describe it, discuss it, but maybe not now. And if you have no filter at all, both methods fail. So the claim is that when we train this neural network initially on 4,000 samples, the main thing that we did, we learned this filter. And once you know this filter, you need much, much less data. So the goal, the work of the neural network, the hard work of the neural network is dimensionality reduction, actually. It's not fitting data. Even though those kind of go together. But it's dimensionality reduction, Once you have this matrix, right, you need relatively little data to get good results. Actually, if you could learn this matrix perfectly, right, it's just a rank 2 matrix, and in dimension 2, you probably need not find the data points would be enough. Okay, so that's basically the kind of maybe the conceptual idea of like what does a neural network do? Now, let me describe this ansatz. And well, if you go back here, you see that NFM and AGOP look very similar. So the claim is, and this is an empirical claim, like we will have proof only for very special circumstances, but empirically this holds very robustly. Basically, the claim is that the matrix is essentially the same. When I say the same, I don't mean they're literally the same. They're proportional to each other. They have very high correlation at point. And well, let me give you some sort of. You can also do it for deeper layers, but let me give you some sort of evidence to convince you that this is actually true. So this is for MLPs, and you can look at this correlation for every layer, and you can see that the correlations are consistently around 0.95. Same thing for convolutional neural nets. This is different, architectures. Again, around 0.9 or so. Same thing for transformers and for things like recursive recurrent neural networks and so on. So it looks like this is happening for like every architecture that is common data. So this shows that these matrices that you get are essentially some sort of low rank filters. Now, what's the upshot of this? It's like, well, okay, so this is nice. That notion of the AGOP corresponds to WW transpose. But why is it important? Well, for one thing, in particular with respect to the input, AGOP is a completely different thing because you're taking a derivative with respect to the input of the neural network, not with respect to the W, to the weights. So this W and AGOP are actually objects of a different type. The derivatives with respect to different things. Moreover, you can treat AGOP of a neural network as a kind of thing in itself, because you can completely just interpret the neural network as being a black box. As long as you can query it, you can compute derivatives. So what does it suggest? Well, it suggests, for example, that we can have new algorithms. And well, how would we do new algorithms here? Well, probably we would like to kind of combine, well, based on the discussion, feature learning with a kernel machine. So that's maybe a kind of mental model for this neural networks. And in this by neural networks, I mean primarily fully connected. You can do something similar for more general architectures, but it's a little bit tricky. Maybe I'll say something about this later. So it's kernel machines plus learning relevant features. And essentially that means that we want to have a function of this form, some alpha I k of m x I m x, when m is some sort of low rank matrix, and you're learning both alphas and m. Well, how would you learn something like that? Actually, it's not that difficult. You start with an ordinary kernel machine, you run the kernel machine, train it, which is just a matrix inversion. And then you extract AGOP from it. Well, what do I need to extract AGOP? It's just a derivative. I need to be able to take derivative, so it's straightforward. Once I compute AGOP, I can filter my data using this AGOP. I'm using a matrix power here. There is some power, but you can, in the simplest case, you can just use Alex. And then I retrain my kernel prediction on this filter data. And I redo. Okay. So very simple process. I just do it a bunch of times. And if you take a Laplace kernel in particular, you can write it down explicitly as equations. I'm going to skip it. And well, it works. And let me actually, maybe let me show you first this one. Basically, at least on tabular data, this works as well as anything. It's very competitive with the state of the art. This is over 121 different data sets. And in fact, it's much faster. Now, let me go back and kind of show you this experiment, which I think explains a lot about what's happening, at least in some of these setups. So this is what, okay, this is not exactly what's called grokking in the literature, but this is a very similar. I'll tell you why. Actually, I won't tell, because I would have to explain what grokking is. And grokking, if you look at grokking in the literature, it's learning modular arithmetic, which is a very different problem from this, but it has a similar aspect. Okay, so what do? We take data. And in this case, this is just two classes from CFAT tracks and planes, and you embed like a little mark here, like a little star. And the color of the star indicates the class. So if you know to look at some of the pixels in the star, you get perfect accuracy. But of course, you give it to the system, it doesn't know where to look at, right? So there is some low dimensional subspace which encodes all of the information you need. But it's kind of hard to get it. So when you train a neural network, what do you see? As the number of epochs increases, you can see that at about 80 or 90 epochs, your training accuracy is already 100%. So from a training point of view, it's perfect. But your test accuracy is still very bad. It's about 75%, right, after 80 epochs. And remarkably, as you keep training, your accuracy, of course, on training set doesn't increase. Well, it cannot go above 100%. But the accuracy on the test just keeps increasing, and it gets to close to 98, I think 98% or something like that. So what's going on? Well, first, this is weird, right? Because if you think of the training being some sort of proxy for test, this is very strange because I already have 100% accuracy. That's where it relates to grokking. I already have 100%. Like, how can I improve? And the answer is that you improve because you are learning that feature space. You're learning features. So what's optimizing your loss function is doing is not actually fitting the predictor data, it's finding that low dimensional subspace. And you can see it visually, because if you just visualize the diagonal of the WW transpose matrix, you can see it's kind of a pretty light star here, and it's much brighter there. Now you can do the same thing with RFM, and it's actually even more striking, because, well, if you just run the kernel, after, so this is the zeros iteration, after you double the kernel once, your accuracy is 55%, which is terrible. It's just a little bit above noise, right? Noise would be 50, random. But you can see that even after 50%, even though predictor is very terrible, it's basically junk. But the feature identification already works very well. And after one iteration, the feature is even better, and you get like 95% after 2 iterations, it's perfect. So it's really learning features. Now you may ask, well, why is that? That a predictor with such poor performance gives you good features. And actually, the answer is the following. Because if you remember the definition of AGOP, this is an average of all of my data points. So even though predictor is junk at every data point, if it's not too biased, then by averaging them, I can average out the variance. So the variance drops. And the law of large numbers will actually allow me to have a decent estimator for the subspace, despite like at every individual point predictor being very bad. So this is maybe kind of thing to think about. So feature learning in neural network is very distinct from fitting training data. It's a separate mechanism. Both happen at the same time, but at different speeds potentially. So you can see at this point, like after say 90 epochs, the accuracy is already perfect, but the feature learning is still pretty bad. Now, what's
I have a question.
Uh-huh.
How do you know when to stop training then? I mean, do I have to have a different perspective about when training is completed?
When stop training?
Yeah, I mean, I'm looking at the training error, correct? And I could keep going on. When do I stop training? How would I know? Do I have to repeatedly be testing the test data as I go?
That's what they usually do, right? They use a validation.
Okay, that's what you'd be doing. Okay, thank you.
There is no obvious way. You cannot, I think, tell from, because on training data, you're already doing perfectly, like long before you get good test results, right? That's what's so striking observation in the original working. But actually, in that paper, they got 100% data, 100% accuracy on training data, and the test data was still random level at random.
And if you were looking at the eigenstructure, even after the training convergence, you'd see those eigenvectors kind of moving around in interesting ways.
The eigenvector, sorry, I didn't quite hear.
The matrix you formed, MM transport or the Agrov, those eigenstructures of that, you'd actually see them continue to evolve as you continue to learn.
Yeah, that's what you're saying here, right? So, well, we haven't specifically plotted eigenvectors here, but you would see that the spectrum separates.
Okay. Okay, thank you.
There is a question, but can you look at eigenvalues of AGOP matrix to decide when to stop? Not in general, because you have, well, you can if you a priori know that there is some low rank subspace, but you usually don't know that, right? In this case, you do, because it's a very simple problem artificially set up. So what you would see that the rank of the matrix is dropping, but you don't actually have any sort of target rank, and you're off to know when to stop. Okay. So that's now maybe I'll use like last few minutes. But you could see when they converge. You can see when they converge, that's true. Oh yeah, I should make one more point here. Sorry, I forgot. With recursive feature machine, with our method, the accuracy is always 100%. So it's a completely decoupled. The accuracy and feature learning are completely decoupled. Because it's always fit. Well, in this experiment, it's always fit just to fit the data exactly. There is no. So accuracy literally tells you absolutely nothing. Even loss tells you nothing, right? Because I'm sorry. It's not that accuracy 100%. The loss is literally 0 because we just. So you can look at the loss; it doesn't tell you anything. So zero loss solution can be somehow very different. It's kind of amazing. That's what we understood recently with this whole story of hollow parameterization. You can have, that's why you need some sort of inductive bias, right? Because you can have different zero loss solutions. Some of them are good and some of them are terrible. Well, the majority of them are terrible. Okay, so let me discuss a little bit what happens for matrix completions. And for this, you need this idea of a structured EGOP, and maybe I don't want to discuss this too much. But imagine I have a structure like this. So imagine I have a matrix now, okay? And my problem will be matrix completion, meaning that I will have some entries, and I want to fill out the remaining entries subject to the constraint that this matrix is low rank. Obviously, otherwise I can fill anything I like. If I don't tell you anything about those matrices, they are. Well, now let me discuss this notion of structured EGOP. And well, so let's think about the columns of this matrix. And let's think that the columns of this matrix come from some mechanism which produces a column. So maybe if you're familiar with topic models, that's a good example. Something like that. So there are some documents which I don't see, and the document like prototype documents, you know, like computers and news and some other thing. And what I'm getting is some linear combination of this prototype documents with coefficients that I can see. And I don't know the underlying documents. Now, if you think that the columns of this matrix come from some sort of other mechanism, then what you would think is that, well, you can define EGOP with respect to each column separately because it wouldn't make sense for me to mix the columns. So the derivative is with respect to that specific column. And then I'm averaging this over the columns. It turns out that this is a kind of good way to think about structured learning. You set up some structure and you do derivative with respect to that structure. You can do basically essentially the same thing with convolutions in the patches. And if you do this, linear and RFM actually becomes the following algorithm. So you have a model, which is f of x equals trace, and you have data. And what is this data like? The data is just an indicator of each position in the matrix and then the corresponding entry. So this would be like, you can think of Aij being ij's location, matrix corresponding to the ij's location in my matrix, and yij is whatever entry I'm observing. So I have a bunch of these observations, but far fewer than this full number of entries in the matrix. And then RFM becomes a following problem of the following algorithm. You first do linear regression. So you minimize, well, you minimize the Frobenius norm of W subject to those constraints. So actually, if you think about it, what is Frobenius norm? It's just a sum squared of all the entries. So it's the first step of this. You would simply put zeros. Well, if you don't know, you put 0. That, of course, is not going to be a low-rank solution, but that's like your first step. And then you are going to do the computation of EGOP, which is happens to have this form. And then you redo this using that. Okay, so it's some sort of reweighting with respect to the previous step. In any case, be it as it may, it turns out that this algorithm is nothing else but a very well-known sort of classical iteratively reweighted least squares algorithm. This is a generalization of that algorithm. And the kind of curious thing is that it's also corresponds to depth L linear neural network, which have been observed to do the same thing. And in some cases, you can prove that they work, but no, there are some limited results of neural networks. Interestingly enough, if you take alpha to be 1/2, so remember alpha is this matrix power that I have in this formula, then this corresponds to neural networks with depth infinity. And if your alpha is bigger than 1/2, then the depth becomes negative. So running this algorithm is like running a neural network with depth -1, for example. It's kind of fun. Now, what can we show about this? You can characterize a fixed point. So there is no, it's not a convergence result, it's a more limited thing. It's a fixed point characterization. So fixed points of this algorithm correspond to the following. So you take your matrix, you look at the singular values of that matrix, and you minimize some norm of those singular values. So for example, rank would be just to minimize the zeros. I guess rank is 0 now, right, of singular values. And the Frobenius norm would be the 2 norm of the singular values, and so on. So what you have is that you basically have the following penalty function on the singular values. For alpha actually equals 1/4, it's the famous nuclear norm. So a lot of theoretical things about the nuclear norm that corresponds to 1/4. And if you actually increase alpha, this function becomes more and more narrow. And for alpha bigger than 1/2, it's actually singular, it goes to infinity. So you can minimize some sort of singular norm, and it still makes, well, if you stare at this expression, you would see it still makes sense. But it's kind of an interesting penalty. Actually, 1/2 seems to work really well, and 1/2 corresponds to log penalty. So it's just the sum of the logs of singular values, which is the same as log determinant, right? Because a determinant is a product. Okay, so you can play the same games with convolutional neural networks, and you can also have a version of convolutional RFM. I'm not going to describe this. I think I'll let me maybe have a couple of slides to summarize. So now I think now we kind of understand at least part of this puzzle. And on the side of the X, on the side of the features, we now see that what modern machine learning methods are doing is this relevant feature learning. So they learn features which are relevant, they do dimensionality reduction, but it's not a generic dimensionality reduction. It's dimensionality reduction with respect to the output. And that makes a huge difference, because if you think about manifold learning, the curse of dimensionality still fits you, because if you're relying on nearest neighbors in the original space and your dimension is very high, it's going to be very difficult to find the nearest neighbors robustly. So that's one thing. On the H side, we now see that we have this benign overfitting in basically the number of parameters, having very large number of parameters is okay. It doesn't hurt. It actually sometimes is necessary. And maybe I'll have a few concluding thoughts. And then, first is that current methods have been developed by trial and error. There is really no reason to think that they're optimal. We should be able to do better. There is, ChatGPT has like 1 trillion parameters. There is really no reason to think that couldn't be reduced to, maybe a billion. In fact, just the other day, there is a new model, GPT-4o, which is, speculation goes is much smaller. The original ChatGPT was similar, but actually better performance. Well, we don't really know, but it's certainly much faster thanks to reason, but it's probably small, a lot smaller. And they're giving it away for free. Or at least that's what they claim. So that means it cannot be that expensive for them to run. In any case, we should be able to do a lot better once we understand what's happening. Second, it is clear that neural networks implement dimensionality reduction, and the kind of general philosophical point we can make from it is that data are far, far more predictable than we used to think. Like, you can, by predicting the next token, you can do math, you can, argue law cases, you can do like all sorts of amazing, write poetry. It's just the next word. There is nothing particularly complicated about it. Once we sort of figure out what the structures are, we should actually be able to do better. And from the point of view of having this alternative, I think at least for MLPs, it is clear that recursive feature machines provide very strong alternatives. And in fact, we have a sort of, from a more theoretical point of view, we have this alternative model, which exhibits many of the interesting phenomena which people observe in deep neural networks, like grokking, neural collapse, things like adversarial features. You can all study them in this way. And what I found very encouraging is that doing it in a linear way recovered this classical sparse algorithm. Was a big area of research. I guess around 2010, the compressed sensing sparsity was huge. And now we can kind of see this connects to this feature. So we can maybe like fold all of this in the same frame of protection. From the thinking theoretically about this, what do we need? Well, first we have to pay attention to empirical evidence. It is clear that without empirical evidence, we cannot do things. And I kind of have been arguing that we need a sort of physics-style approach. We have to look at empirical evidence, build mathematical theories, but we don't have necessarily to prove everything because it's going to be really difficult to prove everything and it will take a long time. We kind of want to have precise mathematical descriptions, but maybe not to prove like every step of the way. Which is a kind of tricky balance, but I think physicists somehow managed it for many years, so it should be possible. And finally, I would like to say that all generalization analysis should scale with intrinsic dimension of the space, and this kind of, it's dual, and by the dual I mean this, I have to spend a little more time to explain exactly what it is, but if you think about the directions of the gradient, you can think of it as something of dual length. And basically, if your gradients live in a low dimensional space, your method should also, whatever the sample complexity you have, should scale with that dimension. Because somehow those are the relevant features. The gradient spans the relevant features. Those are the directions which affect your predictions. And that's the only thing you care about, right? Like if you want to predict the next token, you only care about things which affect the next token. And I think going back to manifold would be very interesting, and that's one thing I would like to do. Okay, I think I'll stop here, and thank you.
Thank you. I have a question, if you don't mind. Hello?
Yes.
Yes. This reminds me of about 20 years ago when people were looking at local linear embedding using eigenmaps. In some sense, you're actually doing this globally. And we look at the outer product of the gradients, that's the classic approximation to Hessians. I know Donahoe was looking about 20 years ago at Hessian eigenmaps. Do you think there's a relationship between what you're doing and that earlier work?
Yeah, so in a sense, well, you see something like Laplacian eigenmaps, you're relying on global proximity of the data, like of your data points, right? You're finding nearest. So how do you do it? You construct a nearest neighbors graph from this high dimensional data. And then you computing Laplacian of that high dimensional graph, which works very well in this kind of middle dimensional regime. When your data are not too high dimensional, your true manifold of data is low dimensional and the ambient space is not too high dimensional. The problem is that when your input data is very high dimensional, your nearest neighbor computation is not reliable. Therefore, your graph becomes very unreliable, and then like manifold learning doesn't help you much.
Right. This is
kind
rather
of,
surprising that you, in some sense, are averaging over all possible input x's. You're looking at some sense an average structure, and it's very impressive to me that it works so well.
Oh, but the average is fantastic, right? Because you're using the law of large numbers. I mean, okay, you're losing, of course, this local structure, which is very nice. And I think there might be ways to keep this. But what is very nice is that you're kind of using this law of large numbers with respect to the output. And that allows you to do this effective dimensionality reduction.
Okay. Very nice. Thank you.
Thank you.
Any other questions? So why do we need deep networks?
Because we don't know how to replace transformers with this thing. Not yet.
Just to clarify, so you're saying that the features are being computed by the initial wave matrix, by the first wave matrix in MLP.
In MLP, I think this is a full replacement. In transformers, the features are being computed at different levels. And it seems that this is really important, that they're computed at different levels. Ansatz still works, but it doesn't lend itself to such a simple algorithm. So in principle, you can replace like the WW transforms by whatever you get from the ansatz, but it doesn't necessarily help you to construct a simple algorithm. That's which I think the algorithm must exist, because there is just no way that whatever they do SGD on that particular structure is optimal. I don't know, it would be shocking. But there are many shocking things to it. Who knows?
Oh, so this example, right, for example, like resonates, since you want to know more intuitively capturing like right features in images. So it's basically doing something like this, but it's
so for RedNet, actually we have a pretty decent version of this for convolutional neural nets. It works. We cannot, unfortunately, replace neural. So right now there are some unresolved issues which seem to be mostly computational, which is very weird, actually. It looks like whatever neural network is doing is more efficient than computing this kernel. I don't know why. I mean, I know why in a kind of very basic level. But I don't understand fundamentally why it has to be true. I don't think it is. I think we don't understand some aspect of computation, which is very no. Yeah.
When you do the deep convolution networks, are you still doing the task where you have a little star in the corner, or are you actually doing object recognition?
In which one?
When you do this on deep convolutional nets on.
Oh no, those are like this is just one example. Yeah, you can do that to manage.
But can you do it with real pictures?
Yeah, you can do it. Yeah, you can do it in C5. We're rather than C5.
I think there are some questions in the chat.
Oh, yes.
I can read it out if you want.
Okay, so there is
Yeah, maybe give me a maybe. Maybe that.
Maybe the last three.
The
last one. That's
Why can we expect the gradient outer product become more and more aligned with data features? Can it deviate from the true features? Well, in principle, it can, but it looks like, so we have some theoretical proof for now for like kernels, but it's much more limited than what's happening. So it looks like it's doing a pretty good job at picking this up. But I don't know. I don't think there is like we have a fundamental proof that it always happens. You can imagine certainly that it will just deviate with something wrong. But it doesn't seem to be so common. Yeah.
So is there a computational, you said there is a computationally intensive state in RFM? Is that the low rank, the factorization of matrix or something?
In RFM itself, no. Oh, well, RFM itself
Because
is
you
just.
gradient outer, but then.
Gradient outer product is cheap, unless your dimension is huge, it's very
But
cheap.
then you are mapping it back to WW transpose and you need W, right?
No, we don't need W.
You don't
For the basic RFM, it's just this. So you build this. This is a single linear solve. The size of this is the number of data points. Then you estimate this matrix. So if your dimension is say 1,000, it's 1,000 by 1,000. It's nothing.
Yeah.
And then you just rescale the matrix,
Just
the data. So you refilter it and then
I
you
see.
plug it in. This is all very cheap unless you're, well, if your data size in the millions, then following linear systems, you need to do various tricks. But it still can be done.
Yeah.
I don't think there is anything like fundamentally difficult here. For what difficulty comes for convolutional neural networks, because computing this kernel needs to be this convolutional kernel, and turns out to be a mess to compute. Yeah.
Okay.
Is there some sort of sensitivity to the choice of the kernel? So it's sort of like the sort of intuition is that like, the option kernel sort of like flattens things out a little faster and sort of mutates some of this manifold structure. Even when you look at it in the embedded feature space, like is there some sort of like intuition of using empirically whether there's a difference in performance?
So until recently, I would always say just use Laplace kernel, because what we have observed is that for almost all problems, Laplace kernel and Gauss kernel give similar performance, but Laplace kernel is much less sensitive to choice of parameters. Recently we observed that for original grokking, which is this modular arithmetic, for some reason Laplace doesn't work at all, and Gaussian works fine. So kind of a little strange. That's what it seems. So there may be some very specific cases when there is a big difference, but in the majority of cases the difference is not that big, and Laplace kernel is sort of preferable just from parameter tuning point of view. That's a purely empirical thing. I don't have anything intelligent to say about why one might be better.
There is a question, isn't this the Fisher information? I don't know which one.
Which one is Fisher? It's not Fisher information, right? Fisher information is with respect to parameters, I think, the derivative. This is really
It's a long
inputs. Yeah. It's a different derivative. I mean, it kind of looks a little like this, but it's a different derivative. Yeah. Yeah, and of course, when you do gradient descent, and your derivative, right, is with respect to W. So when you construct matrix W itself, right, you obtain it by gradient descent. So the process is all with respect to W. And this is saying, the ansatz is saying that somehow the derivative with respect to W and the derivative with respect to X are closely related. At least after you train it.
So I suppose when all is linear, of course, n must be equal to W, not W times W, must be equal.
What's it?
If n is linear, then then you get exactly the only transpose only, so the
If
feature.
purpose linear, then I think it's exactly the same.
It translates,
If
yeah.
it's one layer, if it's two layer linear, it's not.
Right, yeah, if one layer it must be the same. And so here, depending on the kernel you choose, if you use a plus, then what is the space of functions f that we can fit it with this? How crazy can it be?
Oh, it can be pretty crazy. It's a huge space, right? Because you're just allowing like any linear combination of proportions.
But it can have a character.
But the problem is that because you're stuck with something radially invariant. So if your function just depends on one coordinate, but when you compute nearest neighbors, you actually get like all coordinates. Right? And so if all of this other coordinates are effectively noise, right? So you need huge amount of data to overcome that. But once you do this, somehow the law of large numbers comes to help you. And even with relatively small amount of data, you can average it out, find some better representation, then you recompute it with better representation, find even better representation. So,
maybe you can end the talk and we can take questions offline.
Okay. Thanks a lot, Misha.
thank you.
Thank you.